Hey yo, bro, did you know that magnets have brains?
Are you mad? What's with you and random objects having brains?
Bro, just deeper innit? How else would they know that the same poles repel and opposite poles attract?
Now that's because when the magnetic fields interact, they exchange something called virtual photons. This basically transfer information to tell whether the magnetic fields should repel or attract.
Now, in physics, there are four fundamental forces that you need to know about. The first one is a simple one, and that is just gravity. Now, gravity acts between all masses. So, gravity can act between massive objects like planets and stars, but even between two humans or this table and this pen, there is some sort of gravitational force. However, between this table and this pen, the gravitational force is very, 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 very weak. Another fundamental force that you need to know about is the strong nuclear force, and it acts on something called hadrons. And we will discuss what a hadron is in later videos. But the purposes of this is, for example, to hold the nucleus together, and is also responsible for some decays involving hadrons only. The next fundamental force is the weak nuclear force, or often known as the weak interaction, and this acts on both hadrons and leptons. Take these names for granted right now, we will discuss them in later videos, and the weak nuclear force is also responsible for certain decays. Now, the last fundamental force is the electromagnetic force, and this acts between all charged particles. And the uses of these are magnetic and electric forces. Now, these are the four fundamental forces, and you can see I've left this column called exchange particles. Exchange particles are particles that are responsible for these forces acting. For example, the particle that is responsible for the electromagnetic force is something called the virtual photon. For the weak nuclear force, you can have W plus or minus bosons. And again, we'll cover the uses of these in later videos. The strong nuclear force, the particle responsible for this is the gluon. And for gravity, the hypothetical particle is called the graviton. However, it has not yet been found, or it's not yet been proven to exist. Now, these exchange particles govern the behavior of these fundamental forces. Another thing that you need to know are the ranges of some of these forces. Now, gravity and the electromagnetic force have infinite range. They can act over infinite distances. But the range of the strong nuclear force is quite interesting. Now, let's look at a nucleus. We have loads of protons and neutrons in the nucleus. Now, this means that the nucleus is positively charged, and it contains either positively charged particles or neutral particles. Now, a nucleus consists of protons. And they are all positive charges. And we know from simple physics that like charges repel. So, intuitively, these protons should be repelling each other, and this nucleus should not be held together. You would expect that these protons would repel each other and such that the nucleus just expanded and just blew apart. But that's not the case. And the reason for that is this strong nuclear force. The strong nuclear force is responsible for holding the nucleus together. So let's look at the ranges of where this strong nuclear force acts. Inside the nucleus, the protons each experience a repulsive electromagnetic force. And this electromagnetic force has this shape here. It is a repulsive force because the protons have like charges. So this strong nuclear force needs to oppose this electromagnetic force in order to keep this nucleus stable. So in order to counteract these protons repelling each other, the strong nuclear force needs to look something like this. And you can see that this clearly opposes the repulsive force from the electromagnetic force. Now we can say that this section is overcoming the repulsive electromagnetic force between the protons. However, if this force acts too strongly, it also means that these protons could get very, very close to each other. So this initially attractive, strong nuclear force will, at a very close distance, become repulsive in order to stop the protons from colliding into each other. And there are some values that you need to know. It starts becoming repulsive at this distance of 0.5 femtometers, and where a femtometer is equal to 1 times 10 to the minus 15 meters. So the strong nuclear force is repulsive at distances between 0 and 0.5 femtometers, and it's attractive from 0.5 to 3 femtometers. So these are very, very tiny distances at which the strong nuclear force acts over. At distances greater than 3 femtometers, the strong nuclear force does not act. So at 3 plus femtometers, strong nuclear force doesn't act. And this peak on this curve is at roughly 1.2 femtometers. And I think there will be a designated range of roughly 0.8 to 1.5 femtometers in your exam. But I'd stick with a value of 1.2 femtometers for that maximum attractive force. And as we discussed, in this section of the graph, it is repulsive. And that is to stop protons colliding with one another. Now, the best piece of advice I can give you after watching that video is to go off and practice some past papers or topic questions. These are single-handedly the best way to help you commit the content you've learned to memory. Obviously, go and do all the YouTube stuff of liking, subscribing, and if you found this video helpful, feel free to go and watch any of my other ones.